So if you're interested in that, that's good fun. I guess the general theme to these talks is like configuration spaces of objects. So I'm going to talk about, first I want to talk about just affinely natural. And for Pierre's sake, I'm going to try to write things down more than last talk. Natural subdivisions. So if you have a triangle, there's two. If you have an equilateral triangle, there's two natural ways to subdivide it. You can do something like that, or so these are two kind of natural subdivision schemes of an equilateral triangle. And if you wanted to do this for a triangle in general, you could. This is really a construction that just involves averaging. Like this point is kind of the center of these 2 points, and so on. This point is the centroid of the 3 vertices. So you could extend these definitions to any simplex by just using terms that were affinely natural. Now, in higher dimensions, there's, I mean, maybe the most obvious thing to do in general would be barycentric subdivision. So it's defined inductively, and I won't. Area. So the way you barycentrically subdivide an n simplex is you first barycentrically subdivide its boundary, each of its boundaries, and then you cone to the barycenter. So like in this example, the barycentric subdivision of a segment is just a bisected segment. So the barycentric subdivision of a triangle is you first barycentrically subdivide the 3 sides, and then you cone to the centroid point. In 3 dimensions, you would first barycentrically subdivide the boundary. I can't draw it, but you can barycentrically subdivide the boundary, and then you would come to the center of the centroid of the simplex. So this is a way of maybe this is one example. This is a way of subdividing an n simplex into I guess n plus 1 factorial smaller simplices. There's another one. You might wonder, like, what happens if you try to do this? If you cut off the kind of the corners of a tetrahedron, you're left with an octahedron in the middle. So one scheme might be you could cut an octahedron into these 4 pieces and then take the cone on this octahedron to the center. That would be a subdivision of a simplex into, I guess, 12 smaller ones. And again, it's affinely natural. So there are different subdivision schemes. I mean, one reason, I guess, for getting the affinely natural part, one reason you might be interested in subdivision schemes is, I mean, if you were doing some kind of numerical approximation, like you might have something you were looking at on like a function on a surface or something, and you would just compute it in terms of some kind of triangular mesh on the surface, and then if you wanted to get more information about the function, you could subdivide the triangles. And I think one of the things numerical analysts are interested in, well, for 2 dimensions, this thing will work great. You want to subdivide in such a way that the simplices stay essentially round or near the regular one. Because somehow then this makes numerics better. But anyway, but I just got interested in this out of curiosity. So the question is, once you do this once, you can iterate the construction. And here there's no. This one's kind of boring. There's no mystery as to what happens as you iterate the construction. So the main question is kind of what shapes simplices lies in iterated subdivision. So there are different kinds of questions you could ask. Like this has been studied. One question that's been studied by for example, Diaconis and McMullen separately is that you could ask what happens sort of. They have results to the effect that, I think it's McMullen's result, that almost every triangle, as you look deeper and deeper into the subdivision, almost every triangle becomes thin. In the sense that one of the angles goes to 0 with probability 1. So there's a probabilistic thing you could ask, but I'm going to be more interested in the density of the shapes. So just there's some space here, like x is just equal to So,
do you want to mark your simplices?
Well, label. The answer I'm going to get is going to turn out not to matter. But one way to this is, you can think of this as a metric space. I mean, two simplices are close. For example, you could scale them to have a unit volume, and then check and see that you can rotate them so that they're close in the Hausdorff topology. Or put another way, you could just measure every single angle, dihedral angle you see everywhere, and if they're all close, then the simplices are close. Maybe a nicer picture is that if you really use labeled simplices, then there's an isomorphism from, well, I mean, so you could say, so better, say, let's make one scale, just say, label, I'm going to keep adding adjectives. So you might as well take them to be unit volume. And then there's a map from So the map is just you fix some standard simplex, say with the standard bases. And then you give some okay, I'm being a little sloppy. In the scaling, you could rotate or not, depending. I mean, in the answer I'm going to give, it's not going to depend. If you're just allowed to scale, then this is literally an isomorphism. If you're allowed to rotate, then it's really, this space is isomorphic with SLN R mod SLN. So it's not going to matter which I do. So anyway, and then kind of, so the question I want to ask is maybe same question. So this iteration, it gives you a countable union of points in SL and R, and then the question is this a dense set or not? I'm going to talk about what happens for barycentric subdivision, but you could imagine, I mean, the kind of method I'm going to describe will work for any kind of affinely natural subdivision scheme. So far, so good? Okay, good. Okay, so okay, so let me explain how this is related. So let me say some answers, maybe some answers. So yes. So this was a paper this was around 90, I think. So
To which question?
does the iteration produce a dense set of shapes?
Okay, yes, sorry.
Yeah, so this question here. Okay, so yes in 2 dimensions. And then n equals 3, yes. N equals 4, yes, and these are me. So the case, I'll give you more or less the complete proof for 3 and 4, and then I'll kind of, the proof is much harder. I mean, for 2 and 3, it's easy, and then for 4, it's much harder. And then for around like about, I'll kind of argue that n equals 9, I'll say maybe. And then I'll say for n, well, you know, n large, I would say conjecture. No. So I'm going to explain. I'm going to try to explain why for large n this should be probably is no. I mean, but what I like about this question is that it sort of forces you to confront something about the geometry of this higher rank symmetric space. I mean, it's about. I mean, the thing about this higher rank symmetric space is that it has negative curvature in some directions, and then it has flats in other directions, and somehow you're trying to understand, as it turns out, the way a certain tree sits inside this symmetric space. And somehow, if it was negative curvature, you could probably just certainly say no. But somehow the fact you have non-positive curvature influences the answer.
Does the answer depend on the simplex you start at?
No. Okay, so let's address that. That's a good question. So imagine I picked one simplex and I got a dense set of shapes. Then because it's an affinely natural way of doing things, if I applied some linear transformation to that simplex, I would just move the whole dense set by some linear transformation. So for doing this, you might as well start with your favorite one.
So it's just a question about semigroup.
Yes.
Semigroup.
Yeah, that's right. It's a question of whether a certain semigroup is dense. And so let me just say, I mean, for you guys, probably I won't dwell on this too long, but I'll just say a word about connection to semigroups. So you kind of fix label it in some nice way, like so in general, you can label the barycenter of you can label the subdivision of the simplex. You just label the centroids of all the faces, and you label it by the number that's the dimension. Yeah, that's the dimension of the face that contains the point. And then, this gives you concretely, in this example, I mean, in this example, you have a semigroup generated by T1 up to T6. But really, what you want to do is you want to look at so in this example, you would divide by the square root of the determinant to get a matrix of determinant plus or minus 1, and then you'd add a plus or minus to have determinant 1. I mean, some of these would be orientation reversing. So this gives you
n dimensions with 1 over n.
oh. I take the 1/2 power in n dimensions. You take 1 over n.
Yeah, that's what
Yeah. This is just the case for
Yeah,
n
yeah,
equals 2.
yeah, exactly.
So in general, you would have n plus 1 factorial of these linear transformations, and yeah. Okay.
Plus minus, y plus
Well, because when you just divide by the absolute value of the determinant raised to some power, you might get a matrix that is not, it has negative determinant. Right.
Rich just wants to work in SL.
I prefer to work in SL and R rather than SL and R union, SL and R minus.
minus
But
1.
if you still have the plus or minus still might not help. So it depends on your dimension. 'Cause that means you multiply your matrix by minus 1 to the n, if n is even. And that's
Okay. Good point. Okay, you know what? Let's just work in SL and R.
I think
Plus
we
or
can you just decide?
Oh, so I guess each, well, okay, so maybe these will have,
swap 2 of the columns around or something.
no, I don't want to do that. Let's just have it be matrices with determinant plus or minus 1. Okay, this is a perfectly good. Yeah, but you're right. I always make that mistake, and I made it again. Okay, so but it's, I mean, if you look at words of even length, then you're in SL and R for sure. Okay, so I just want to point out that you can have a dense group, but you can have a non-dense semigroup that generates a dense group. Like so just sort of note, x goes to x plus 1 and x goes to x plus root 2 generate a dense group, subgroup of R, but not a dense semigroup. And another, just you can also rig up examples, say in SL2R. Like for example, you could pick two hyperbolic translations along very clear, geodesics pointing in the same direction, so that so I call this like G and H, so that GH inverse is elliptic. So you could pick two translations that are almost going in the same direction, so that when you do one times the inverse of the other, it's infinite order elliptic, and then you could pick two more, which would give you a second infinite order elliptic fixing a different point, and then those two would generate a dense group. But all the translations would, if you just look at the positive words, they would just push everything over in this direction. So again, the semigroup would not be dense, but the group would be dense. Okay, so that can happen.
There are several ways to label. And does this have any importance?
it doesn't really have that much importance, because if you were to change the labeling scheme, you would be more or less just conjugating the group by some finite group. Yeah, so it's not important. Yeah, I mean, it's a geometric, I'm interested in a geometric question, and it's not going to depend on this. Okay, so I guess it's too bad data walked out. There's some general areas. Yeah, there's some general fact that if you have a in SLNR, if you have a Zariski dense group it's either, I guess it's either just discrete or dense. So it'd be pretty easy to show that a group is. I mean, I didn't actually do it this way. So one lemma is that I have to give it a name. So I'm sorry. So let say let. And then let So the first lemma is that so let me try to explain this. I mean, if you want to invoke this theorem this general theorem, you just need to show that this thing is not discrete. But let me explain what you can do in general. I'll just give you an idea why the group. So this is just sort of a general. So imagine. So if you do barycentric subdivision on a particular simplex. Here, let me draw a picture. So I can pick two simplices that share a codimension one face, and I can call them A and B, and I can look at T of A and T of A, T of B, and then I can look at well, I want to hedge my bets because pick A and B that share either a codimension one face or a codimension two face. I think I want a codimension two face. And the idea is that T sub A prime, or TAT B inverse fixes this large codimension space. And so it really just, all of the action of this element is just happening in a very, sort of in this kind of two-dimensional normal bundle. And so you can just work out for explicit choices that you find, if you pick the right A and B, then the element you get is an infinite order rotation in the normal direction to this fixed codimension 2 plane. So just by a kind of a direct calculation, you can see that there's an infinite order elliptic element in this in the group. And then, I mean, how would you prove this by hand, that then the group is dense? Well, I mean, the closure, it contains elements of arbitrarily small order, so there's some element in vector in the Lie algebra, which more or less is hit by this subgroup, and then you can start conjugating this around, and you can get many elements in the algebra, and then you can just generate the whole Lie algebra, and then you get the whole group. So it's not. So once the basic idea is that you look at an elements one times the inverse of the other, where they fix simplices that share a high dimensional face, and then it's easy to analyze the one times the inverse of the other. Okay, so this is dense. So,
So in dimension 2, am I supposed to see on the picture why you did?
no, it's a calculation. Yeah, I don't have a good reason for this. I just, yeah. Anyway, the paper's published, I mean, you can just, or I can, there's some crazy calculation, which in fact, yeah, okay. So the second, okay, so the group is always dense in every dimension. So then lemma 2 is that if Sn has a bounded walk, then Sn is so let me sketch a proof of, so what do I mean by a bounded infinite walk? I just mean, you have the semigroup and so I just mean an infinite word, and what I mean by a bounded infinite walk is, I mean, if you keep truncating that word, so I have like ti1, ti1, ti2, ti1, ti2, ti3. So these should be bounded. So this is what I mean by a bounded infinite walk. I mean you have an infinite word and you just keep looking at successively longer finite portions of the word, and those should just be a bounded subset of S ln R. Makes sense, right? So so what's the idea of the proof? I mean, imagine some kind of sketch. Well, so maybe I'll just draw a picture. I mean, imagine that some of these words were very close to the identity. Okay, so imagine you have a very long word that's close to the identity. Maybe T, I1 up to. Then what that means is that you can express Ti1 inverse is approximately equal to Ti2, Tin. So if these things not only were a bounded walk, but they were getting close to the identity, then the inverse would be in the closure of the semigroup. And so, imagine you could get a bounded walk that started, I mean, there's a little bit of fooling around, but this shows that at least one element in the group is dense and is an accumulative.
Rich, you're assuming that this bounded infinite walk is like, when you were at Curry, it's different from like the identity. I mean, like I'm just saying, like in a sort of a silly case, you could have A inverse, and you could have B in your semigroup. And A inverse could like move things back and forth discretely along this line here. And
Well, that's okay, then B inverse would be, oh yeah, okay, all right, so let's say more about this. Okay, let's say more. So imagine that every, not only is this a bounded walk, but every finite string appears in the bounded walk. Or not every finite string, but imagine every particular element
That's
appears infinitely often. In other words,
well, what I'm worried about is that, like, I mean, the example I said, like the group it generates could be discrete and not dense, for instance.
well then some element would be an inverse of another, and you would have recognized an element as an inverse.
Well, okay, but that's not what that by your number. As I said, we have a semigroup which contains A inverse and B. And it could very easily be that it generates an indiscrete group, but that A inverse and B is generates something
Is the and hence in your lemma part of the lemma or merely a conclusion from this lemma combined with the other one?
Okay, it's,
You want the walk when it comes back not to come back to the same, literally the same place.
well, no, I don't mind. Imagine this was equal to the identity.
Yeah.
Okay, so imagine this was equal to the identity. Then I could say that this inverse was,
Yeah, you have the inverse of at least one element, but maybe only one.
right, but what I want to say, okay, imagine, but, okay, this is,
Can you explain the example?
It could be just a finite group, you know, when we say it could be.
yeah, you can get one. I mean, okay, so I'm kind of giving a toy proof, which I don't actually have. So here's this.
If you had a finite subgroup, you could then,
You could use that.
you can use that to make a bounded infinite walk, I guess that's what it says. If you
Yeah.
had a finite subgroup.
If you want to say like, for any prefix, every
Yeah.
prefix is a prefix of a bounded infinite walk. How about that?
And that's true. Yes. That's gonna. Yeah. Okay. Good. That's gonna be true. I mean, what really is gonna happen is I'm gonna have a bounded infinite walk, and there's gonna be various pieces that are close to the identity. I'm gonna be able to pick off that particular letter. Now, in the case of barycentric subdivision, all of the elements are conjugates. So in fact, if I can recognize one of them as the inverse of the others, I can get all of them by symmetry. So at least in this example, you can it's enough just to, you know. But if you have a bounded infinite walk, then there's going to be very long stretches of words. So let me give the proof now, even though I agree with you, just for barycentric subdivision. So imagine you have a bounded infinite walk, there's going to be arbitrarily long strings which are close to the identity. So you can express at least one element inverse in the closure of the semigroup. But then by symmetry, you can express all inverses in the closure of the semigroup. So we can argue in general. So this is not going to be a good lemma in general, but at least in this case. And you'll see when I give the construction that you can do this, you can start with any prefix and you can get a bounded walk.
Right. So I mean, for dimension 2, it's kind of clear, right? Because if you have a triangle that's very long and thin, there's sort of something in the subdivision which is a bit better.
Not so clear, but maybe.
Right? Something in the subdivision is sort of either more balanced or definitely less skewed.
Yeah, probably. Okay, so for 2, yeah. So here's, okay, so anyway, let me just say this again, so just in case. So anyway, if you have a bounded infinite walk, then there's arbitrarily long strings which are near the identity, and then you can, get at least one element, and then you can get the rest. And then the hence is because of the other result that they group. So
It's if and
yeah, right. It's in one. Yeah. Okay, so so now I can give the proof in 2 dimensions. Well, let me say something experimental. Like, well, okay, so what happens for n equals 2? If you label right, and it's the labeling that I described before, then all ti prime are infinite order. So that's the end of the proof. It's just a direct calculation. You just check the trace of the matrices between 0 and -2 and 2. Or maybe if you really want to do it right, you should take the square of the matrix just to make sure you're in SL2R. So there's certainly a bounded infinite walk. You just take single power. So that's the proof in 2 dimensions. So for n equals 3, there's a fact. A computer search reveals some So it turns out that there's some words of length 3 that are infinite order elliptic. This is sort of kind of a very lucky accident, because the thing about SL2R is that the set of elliptic elements is open in the set of all elements. And so if you really did have a dense group, semigroup, then eventually it's going to turn up some elliptics, and with any luck, they're infinite order. But for SL3R and SLNR for n greater than or equal to 3, the set of elliptic elements is a positive codimension subset. So it's sort of lucky that you get, I'd say about 1% of them. So sort of about 1% of the words of length 3 are infinite order elliptic. So that proves it for n equals 3. Just it's a calculation. But I mean, what I really want to talk about is n equals 4. So what do you do if you don't have good luck? Like, these are both cases of good luck. So
here you're literally looking at, this nice symmetric affine. Sort of
Yeah.
I mean, you could perturb very slightly what you meant by.
That's why I'm going to describe this other method. Yeah. That's why. So I'm going to give another method, but I want to say something experimentally. There's an algorithm you can do to look for a bounded walk, where basically you have some, notion of roundness of the simplex, like the norm of the matrix or something, and you could try to walk greedily in the semigroup, like just pick elements and pick whatever one next, which is going to minimize the kind of product norm. In terms of the symmetric space, it's like you're trying to kind of get back to the origin as best you can. And this works up to about dimension 9. Experimentally, it seems that up to about dimension 9, there seems to be a bounded infinite walk just using the greedy algorithm. I got a little ambitious and I tried some fancier version of the greedy algorithm where I picked, like, you could kind of look at, say, words of length 2 or 3 and pick the best combination. I mean, eventually you're defeated by just the depth of the search. But anyway, then somehow, like around, I think in dimension 9, you can't find a bounded infinite walk. So let me give some intuition. Maybe before talking about the proof n equals 4, I want to say a word about why it seems to me this ought to be false and why it's not dense in high dimensions. So you can embed this semigroup as a tree inside the symmetric space. So this is SO and mod SLN. And you just pick an orbit, and then you have. Okay, well maybe I don't need to dwell on this for this audience, but anyway. And the thing is that in the translation lengths go to infinity the lengths of the tree go to infinity, and the number of branches is like n factorial, and the dimension of the sphere is like n squared, or n choose 2. And so there's a question, like there's this fact that if you have like a very high dimensional sphere in n dimensions, and you pick, say, spherical caps of size definitely less than 1, then you need like e to the n of them to cover the sphere. And if you have a sphere dimension n squared, you have to take like e to the n squared points to somehow get a good covering of the sphere. And we're talking about n factorial points and kind of directions distributed over a sphere dimension like n squared. And n factorial is a very small number in this context. So somehow it's like you're kind of not really going in that many directions, and you're also taking long strides. So it sort of makes me feel like you just are never going to get back. Somehow the flats in this space cause some kind of problem, because you could sort of imagine that like things were just timed so that as you moved down along this tree, you were kind of staying very close to a flat. Then in a sense, you would actually turn around.
Wouldn't I only have to have a few clusters that were close to each other on the boundary to be able to sort of, or almost opposite on the boundary to be able to kind of approximately back up and get some nearly elliptic, and then.
Well.
You know what I mean? Like,
Yeah. I don't think that's. Yeah, I don't think that.
If they were nice and randomly
If they-
distributed, maybe, but, I mean, aren't they kind of very highly anti-curvature?
Yeah, okay, well, it's a good point. I agree. If there are some that are, this isn't really such a strong argument, but I
I'm
mean.
just saying like a dimension count or something, gives you
It's sort of like the first example I gave. Well, yeah, I mean, you go out and then you can imagine trying to come exactly right back. I'm not sure. I don't really understand the geometry of this tree very well. Anyway, but I don't have any results about this. I just noticed that the greedy walk fails and, above dimension 9.
Is it a free semigroup?
Yeah, it's a free semigroup. Yeah, so basically you have this embedded tree and you're walking along. Okay, so,
Why is it clear?
You mean it's a map from a free semigroup? You don't mean that you've verified that there's no identities amongst your generators?
oh yeah, that's right. I mean, okay, yeah, you're right. I mean, I don't know that that's right. But, like here I found some elliptic elements of order 3. So in this case, they're infinite order. But you can imagine you get even luckier and, it's finite order or something. I mean, I couldn't find any elliptic elements in,
You find finite order ones?
no, I couldn't find any finite order or.
It could very well, it could be that it's free.
Yes, I would guess, I conjecture it's free for n greater than or equal to 4. Yeah. That's right.
And for 3, even for 3.
Oh, it's not. I guess I would actually conjecture it was free for, well, yeah, I think it's free also for n equals 3. I don't know how to prove that. Like, that would be nice to prove that there are some, either are or not some relations, but I don't think there are.
Is it obvious in dimension 2?
No, it's not completely obvious. I mean, you have, although it's pretty explicit group. I mean, you have these 6 infinite order elliptic generators that are arranged in like a little hexagonal pattern in the hyperbolic plane. So you're asking if that particular semigroup is free. And my guess is again yes.
Okay.
Yeah, okay. I didn't try to answer this question, but I mean, thinking about it now, I can't see how to answer this question.
What about even the group?
Oh, what's the group? Yeah, I don't know about the group either. I mean, I didn't look at the group at all except to prove that it was dense by looking at these specific elements that were infinite order.
And the entries are like quadratic irrationals, right? They're not that big.
Oh, well, okay, so if you forget about the scaling, they're rational.
Yeah. So
They're
that's-
rational, but then you're
not very
dividing by the determinant, so. Yeah, so you're taking the nth root of some real number. Yeah, so they're.
So, I don't know, I mean, like, there could be some, you could look for, whatever, you could look for relations, and there's lots of finite quotients where there's lots of relations.
Yeah.
You could do a computer search. is my point.
Well, okay, so the numbers are kind of funny, right? I mean, you're taking the nth root of a.
Yeah, but what I mean is you could look at, there's lots of finite quotients.
Yeah.
And so you have lots of elements that you know go to the identity in those finite quotients. So
Yeah.
those are particular things, give you very good candidates to look at to be the identity of.
Oh, I see what you're saying. But I mean, it's a free,
It's a
yeah, there's
finite-
many, well, but there's so many quotients. I mean, you can just, right? I mean, yeah, there's a lot of quotients. I mean, it's just a free group. Okay, anyway, I don't know how to, the problem with this is that the number of generators is n factorial, let's say 5 factorial or something like this. And then somehow like, you're not gonna, maybe you're looking at words of length 10 for, this is like 5 factorial to the 10th power. So this is like 110 to the 20th power. I mean, this is probably beyond computer tech. There are no computers fast enough to do a search like that. So even fairly modest questions like that are computer, I mean, no, I'd love to be able to do it. I mean, but I mean, somehow you're kind of stymied by this super exponential growth for computer. Okay, so I'm gonna tell you guys how to do it. And this isn't gonna take a full another hour and 15 minutes, but maybe it'll take like 25 minutes or something. So is everyone good so far? So here's a definition. Okay, anyway.
Is everyone but Danny good?
So here's a definition. So let, X. I don't know how to write this. Maybe I should put this down here. So people have different ways of thinking about this space. I think of it as a space of unit volume ellipsoids in Rn, and then the origin is the round ball. Anyway, so what's a horoball in this space? A horoball is just a geometric limit of increasingly large balls, provided the limit's not the whole space or empty. So definition. Say special horoball is one. So here's a picture of a special horoball. There's X, there's O. So that's what a special horoball is. It's a horoball that contains the point, the origin, and its boundary. And another definition, a set, say, W subset X is a steering wheel if every special horoball contains a point of W units. So in other words, I'll draw a picture. Like this would be, so a steering wheel is a property, it's a finite, I'm thinking of it as a finite set of points. It doesn't have to be finite, but it might be. It has the property that every special horoball contains at least one of the points in the interior. So this is sort of a way of saying that the steering wheel kind of has a lot of points in it. Does it make sense? Yeah.
So your horoballs are allowed to be centered at, your special horoballs are allowed to be centered at any point in infinity?
Yes, but the boundary go through the boundary always contains the origin. So if
But
this,
you are allowed every horoball.
it's only, the steering wheel, it must work for every special horoball. Every special horoball has to contain a point of the steering wheel.
So the special horables are just the directions away from the origin.
Yes, exactly.
And this is a way of measuring the neighbourhood of that direction.
Yes.
I think.
So what it's saying is that you go out in any direction and you're gonna encounter a point of the steering wheel. That's what it means. So just by compactness, what it also says is that there's some sufficiently large radius so that if you have a ball whose boundary contains the point, then it also contains a point in the steering wheel. And the point is a definite radius amount inside the ball. So that's just by compactness. So then definition S semigroup is steerable if So steerable
the definition of it is that then it is a steering wheel. Yeah, a steering wheel. If you make the set larger, it stays.
Not necessarily.
But-
Like, I mean, let me give an example of a semigroup that does not have a steering wheel.
No, a definition of a steering wheel means that if you make the set larger, it is still.
Yeah, certainly.
Yeah. So,
Yeah.
So contains means it is.
Well, yes, but I might, yes, I mean, but, okay.
You want
It's
to
steerable
look
if it is a steering, right, logically you could just say it's steerable if it is a steering wheel.
But you want to.
But I want to have a finite set that's a steering wheel.
Okay.
Yeah, I mean,
Yeah. Sorry.
I'm interested, but I agree, like, once, you know, so let me sketch the proof. The lemma is that if S is steerable, then S has a bounded infinite walk. So let me give the proof. So I've got my tree in a symmetric space. I'm trying to find a bounded infinite walk. Now, by symmetry, okay, so imagine I just pick, like, if Danny was here, he would approve of this. I can take any prefix I like. So I start walking around on this tree, and after a while I get pretty far out, and I'm getting a little nervous, like I'm too far from the origin. So I want to come back to the origin. So what I do is I take a metric ball that goes through my point and the origin, and then I can find a point which is which is inside, and move closer to the origin, and by a definite amount. And now I can just keep doing this for a while, but eventually I'm not going to encounter any points in my steering wheel because I need to use really big balls to find them. So then I wander around randomly for a while until I notice that I'm really far away from the origin, and then I, again, can use the steering wheel to move closer to the origin. So this has a lot of flexibility. I mean, I can more or less pick any finite prefix, and I can put it anywhere I want in this word over and over again. And so, yeah. Does that make sense? Okay, so all I have to do to finish the proof that my semigroup is dense is to exhibit a steering wheel. Now, what I'm going to do is I'm going to use hyperbolic geometry to do this, because this symmetric space is somewhat difficult to work in because it's hard to say what the parabolas look like, and so on. So the next lemma is it's a comparison lemma. I guess it. So here I've got my space xn with the origin, and here I've got hyperbolic space of dimension basically n choose 2 with the origin. So just use some standard model of the hyperbolic space. And then there's a map between them, which I should call the Hadamard map. So the Hadamard map, it maps the origin to the origin, and it identifies the tangent spaces at the origin isometrically, and then it maps geodesics to geodesics. And it's normalized so that with the curvature right, so I pick the map that maps the origin to the origin and then just maps geodesics. I use geodesic polar coordinates, in other words. And I just normalize so that the inner products at the origin are just the Euclidean inner product. And then the thing about this map is that this map is distance it's distance non-decreasing. That's what you get from the curvature condition. And the basic reason is just from what's familiar from Riemannian geometry is that the sectional curvature is basically governing the growth of the Jacobi fields. And more curvature is more negative than the Jacobi fields are growing more rapidly. Okay, so here's the thing. The important point is that if I have a special horoball in xn and I map it, what's the set look like in H and n choose 2? It's fatter than a special horoball. It's because the distances are expanding, or a metric ball. Another way to say it is that a metric ball, this point here, this distance is preserved, and then the radii are going up. So the image of a metric ball through the origin is let's call it a fat metric ball. It contains the metric ball of the size you like. So imagine I've got a set here which I am hoping to prove is a steering wheel. So I map it to here using the Hadamard map, and if I can verify it's a steering wheel here, then it goes in the right direction. So it's contained in every ball has one of these things, and so every fat ball has one of these things, and so every ball has one over here. So to prove that I have a steering wheel in this funny symmetric space, I can just transplant the problem to hyperbolic space.
So what's the map again?
What?
I didn't get that. This map. What is this map?
So in Riemannian geometry you learn about geodesic polar coordinates. So this is the standard map from Rn. So this is the composition of geodesic polar coordinates with the inverse of geodesic polar coordinates.
There's a log followed by x for Riemannian metric.
But
Yes.
how many? What n choose 2?
Because that's the dimension of this space. I picked the hyperbolic space that has the same dimension as the symmetric space.
Oh.
So the dimension of this symmetric space is like n choose 2. Maybe it's n choose 2 minus 1. I mean, yeah, it's probably n choose 2 minus 1.
Right.
I mean,
You want them to be diffeomorphic to be able to do
I want them to be diffeomorphic.
Okay.
Yeah, so in my case, the dimension is 9. Yeah, which is not n choose 2. 9. Okay, so anyway, so now I'm reduced to this question: how do I verify that a finite set of points is a steering wheel in hyperbolic space? So I'm going to reduce this to 2 problems. First thing, I'm going to reduce it to a sphere covering problem, and then I'm going to just explain another problem. I could lie and say I reduced it to a sphere covering problem, and then I algorithmically solved the sphere covering problem, but I didn't actually do that. I did something that was computationally nicer. So let me explain how this is related to sphere covering. But let me say the end of the talk first. I found a steering wheel with 144 elements, and each element had length 144. And that would seem to be the shortest I could find. So I computationally found a steering wheel, and that finishes the proof. But let me explain how this is related to some computational problems.
So it's in SL4?
What's that?
SL4?
Yes. Right. And I used a method. The way I found these elements, maybe I'll say that first because it's kind of a neat thing. I mean, there's this Margulis lemma, where or this fact, or the proof of the Margulis lemma, where if you take commutators of elements, they tend to get shorter. So I have a semigroup. So what's the Margulis lemma for semigroups, or what did I think to do? I thought of looking at products of elements A, B, C. So what I would do is I would maintain a list of like 100 or so elements that were pretty short. And then I would take them in triples and I would breed them, so to speak. I would do A, B, C, and I'd see if it was shorter. And the intuition about Margulis lemma is more or less if you go around almost a square, you're coming back closer to the origin. And here you're kind of going around a triangle. And anyway, this worked. I just ran this kind of breeding process. Well, I picked the 100 best, and then the words would be 3 times as long, but they'd be better. And I would do this again with the 100 or so best. And then after I stopped at 144 and I was able to verify that I transplanted it into hyperbolic space and I was able to verify that it was a steering wheel. So let me explain. Let me explain why. Like so look. So here's so now we're just in hyperbolic space. You can forget about this weird symmetric space. So imagine I have these points. So here's my. I'm going to work in the ball model. So here's the sphere of radius 1/2. And here's a torus ball, and it's centered at the point y. And and I've got my supposedly steering wheel, say W is W1.
It's Euclidean radius 1/2, not hyperbolic radius.
Yes, it's Euclidean radius 1/2. I'm sorry. It's the
I
thing.
automatically had hyperbolic.
I'm sorry. It's the, right. It's who knows what the actual Euclidean or the actual hyperbolic radius is.
Yeah, sure.
So let's call this horror ball like H sub y. So Wi is in H sub y if and only if Wi minus y is less than 1/2 in the Euclidean sense of the word. And so now I can introduce these things, which I'll just say, say theta sub j is the set of y such that Wj minus y is less than 1/2. So we can say that Wj is in Hy if and only if this is true, which is true if and only if y is in H sub j. Okay? So all I need is that S, the sphere of radius 1/2, is contained in the union of the theta sub j's. So what is theta sub j? Theta sub j is some other metric ball, and it intersects the sphere of radius 1/2 in some other metric ball. And so to verify that I have a steering wheel, I have a kind of potential covering of the sphere of radius 1/2 by balls, and I'm trying to show that it's a cover. So that's a sphere covering problem, and I'll lie and I'll say that's how I solved it. But let me explain what's nice about this problem. How do you show that something's a sphere covering? Well, I could show that this is a sphere covering. I could take each theta sub, say theta sub 1, and I could look at all the other thetas that intersect it. And as long as all of the boundaries of all of the thetas are covered by boundaries of other ones, then I'm done. So if I have an n-dimensional sphere covering problem, I can solve it by breaking it up into a bunch of n-1 dimensional sphere covering problems and so on. So the sphere covering problem is a recursive thing, and I'm only in dimension 9, and so in principle I could just reduce this to a bunch of smaller sphere covering problems and do it. And so I'll just lie. Let me just lie a little bit and say that's what I did. But I didn't do that. So I'll give another criterion. So I won't give a proof that the criterion works, but I'm going to give, I'll give a sufficient condition for the sphere covering problem to be solved. So here's, so I'll bring this up. So what you can do, I've got my, I'll tell you what you do. So I compare two things. I have my, here's my candidate steering wheel. So what I do is, I first take the smallest ball centered at the origin that contains them. And then I take each of the points and I just go out on a straight line till I hit the boundary. Oops, like this. And then I take the Euclidean convex hull of these points. if you like the hyperbolic geometry, you could take the hyperbolic convex hull and Klein model. And the lemma is that if the convex hull of these points on the boundary contains the ball, then it's a steering wheel. Then this sphere covering problem is solved. So all you have to show, so how do you show that a ball is contained in a convex polytope? Well, okay, well, you can exhibit as, I just exhibited some smaller, it has 144 vertices, it's a pain. I just sort of exhibited some smaller, like a cross polytope, more or less, that contain the ball. So I kind of found a sub-polytope with many fewer sides, which contain the ball. So I just verified this criterion, and then there's a little argument that says that if this criterion is true, then the sphere covering problem holds. And so therefore, you have a steering wheel in hyperbolic space, and then by the comparison lemma, you have a steering wheel in the symmetric space. And then you have a bounded block, and so therefore the semigroup is dense in the group, and the group is dense, so therefore QED. That's it. Yeah, I mean,
when did you use this dynamics? So this iteration in the
oh, because the dynamics is just encoded in the fact that you have a semigroup.
Yes.
And so, I mean, I also used it, to produce this steering wheel.
But in the end of the argument, when you pass to hyperbolic space, you used to the.
Oh, the dynamics is gone. I mean, all that I did was I used the semigroup to find this particular steering wheel. And then I wanted to certify that it was a steering wheel, so I mapped it into hyperbolic space, and I used this convex hull criterion. I don't know. My guess is this is a well-known criterion, but I made it up myself. Didn't see it anywhere. So all the dynamics. So firstly, the dynamics comes up just in the fact that you do have a semigroup. But then secondly, I use this kind of. I don't want to dignify it by calling the semigroup Margulis trick, but anyway, I did this thing with triangles to kind of keep producing words that were shorter. This criterion, you want the words to be small because the intuition is like if the words are small, you can really kind of go all over the place. And I just kept using this triangle trick, using triples of words to keep shrinking the points.
So you were running sort of this dynamical trick of iterating, looking at triples up in the symmetric space, and then you're mapping them down to a hyperbolic space and using this
Yes.
to verify that
Right.
eventually you found a steering wheel.
Yes.
Okay.
Yeah, so you could imagine this would be a little bit painful by hand, but basically I would run this thing and I had some sense of the sizes involved. Really, it's 144 elements, but there's a big group of symmetries. I mean, the symmetries of there's some finite group that conjugates the tree is symmetric under some group of so really I think mod symmetry there's only 3 words in the steering wheel, but they have like 144. Yeah, it's exactly what you said. I'm just using this trick. I'm breeding these matrices. I'm making them, getting small elements that are fairly well distributed, and then when I'm happy enough, I just map them into hyperbolic space with, some explicit map, and check this kind of computation.
So is there something going on here that looks like if you're doing this iteration just to find nicely distributed elements in some ball around the origin? Is there some sort of, do you think there's some sort of equidistribution going on if you keep running this iteration, they'll sort of cover all directions?
Well, I mean, after the fact, it's a dense semigroup, so yeah.
Okay.
But, probably this thing is really nicely equidistributed.
The fact that you're finding things around 144 makes me think there's some equidistribution happening at a fast rate.
Yeah, this triangle thing was very, very efficient. This just boom, boom, it just nicely, and you have this large symmetry group, so once you find one, there's a bunch of other ones, because you could just, there's the group of the affine symmetries of the simplex, and that gives you a finite group that kind of sort of an automorphism of the semigroup. And so once you have one short guy, you can just sort of move it around by automorphism and get others. So that's accounting for some of the, so I just found 3 reasonable ones, and then there was symmetric enough to do it. Yeah, Srini?
So do you then self-similar action of the same group or you
Self-similar. Yeah, what do you mean by self?
multiplying or adding an extra word and the action group just translate it on this word. Find them of the group that action is one word.
Wait, I mean, I don't know if this is any different than any other free semigroup like this. Yeah, I'm not sure what you're saying. Like, I mean, you have this tree, which is, I mean, it's not self-similar. I mean, it's sort of, but each branch is isometric to the whole thing. Yeah, each branch is like, right, I mean, this thing just kind of goes off, and wherever any future cone is just isometric to the whole tree. So yeah, I mean, in that sense, it's self-similar, although, you know, I don't know. I mean, I wish I could sort of see in high dimensions, like, how does this thing accumulate on the boundary? I mean, yeah, I'm guessing, like I said, I think the answer is it's not dense in high dimensions, and so I'd expect some kind of interesting thin set, but.
But it's not discrete, right? Because it's small dimensional. It's not a discrete set, right?
No, it's going to be some, no, I mean, right, if it's not dense, it'll be some weird
Because
fractal
it's got-
subset.
It's got non-discrete
Yes,
subsemigroups.
yeah,
Restrict to a face.
yeah, it's not, right. Yeah, but you know, yeah, I'm picturing it'll look like there'll be a Cantor set of ends. But again, I just, I don't know how to answer the question.
Do you have it? Yes, what's the heating measure?
I mean, okay, so I should say, you know, McMullen studied this in 2 dimensions. He looked quite a bit at like what this, you know, how this thing accumulates on the boundary. I mean, you know, he proved this result that like almost every triangle gets thin. And I mean, I think Diaconus also has a, so I know that they thought about like, you know, from a measure theoretic point of view, like what happens. And, you know, they have, well, I'd have to look at their papers to really tell you, but there are these papers that they wrote in the literature. You know, it's that they've talked about this in low dimensions anyway.
What makes you think that the answer to your question is negative in high dimensions?
Well, because when you look at this tree, the branches are long. I mean, Danny may have debunked this argument, or you know, the branches are long, and there's not that many directions in comparison to the dimension. I mean, there's like n factorial directions, but the sphere is dimension n squared, or n squared over 2. And somehow that's not a lot of points on n factorial is a small number of points on the unit sphere of dimension n choose 2. Like, you need many, many more points than that to say cover the sphere with spherical caps of diameter 1 minus epsilon or something.
So if it's happening there, it's happening for, it would have to be happening for some kind of weird reason.
Yes.
It's not the reason you're seeing.
Right. I mean, there's this, in fact, like concentration of measure considerations. Say, like, if you kind of randomly pick points on a high dimensional unit sphere, they're basically orthogonal. You know, they're almost surely orthogonal. So if you just think about this thing as kind of random, you know, then you're more or less have these very long branches and you're going out in orthogonal directions. So it looks very much like, yeah, like you're taking a right angled broken path, and this thing is surely going to go out to infinity. But that's not really what it looks like. But I can't picture what it looks like. I mean, it's, you know, it's like, you know, yeah, I mean, there's some, yeah. You know, it reminds me like sort of, it's a slightly different subject, but you could ask like, what's the asymptotic cone of a high dimensional cube look like? Right, like, can you picture that? I mean, this is a similar kind of question to me. Yeah.
I think I'm mistaken. If you fix, it's not like if you know, if you fix a face and you when you look at the barycentric division, fixing, stabilizing a face and fixing the opposite vertex, it's not going to be as a replica of the smaller dimensional sample.
No, that's right, because, I mean, there's this other direction that comes in.
Right. Otherwise,
Yeah,
density for n equals 3. would
Yes.
minus density for
yes.
So there is a chance that it's a discrete set, right? It's a discrete sample. It might be a discrete sample in higher dimension.
Yeah. Yeah, that's what I think, actually.
Even uniformly discrete.
The sum total of my evidence is that like above 9 dimensions, the greedy algorithm produces a divergent walk. And even somewhat enhanced greedy algorithm. Yeah, I tried pretty hard to figure out how to get a bounded walk. But the fact that it's sort of like, well, at some point I put a student on this who sort of also did some kind of enhanced greedy algorithm, but he couldn't find one either. So there was some kind of explosion in the statistics, like below dimension 8, it's very good, and then like at dimension 9, it just, whatever you do, it just kind of runs off to the boundary quickly. So, I mean, I wish I had more computational power.
So wait, why is 9 more than 5?
I mean, the symmetric space is like, 9 times, it's like 35 dimensional or something, I mean, I don't know why 9's important. It's just some kind of, it's just when.
What did you bring it up? Why did you say 9?
Well, because because I've reduced showing it's a dense semigroup to finding a bounded infinite walk. So if you might not be interested in proofs just for the first pass. You might just be interested in evidence that there's a bounded infinite walk, and a natural thing to do would be to try to do it greedily, which is more or less all you can do because it's too high dimensional. So you take a step and then you try to take the step which brings you closest to the origin. And this works up to like dimension 9. You can just run the computer and you can see it stays bounded.
Okay, so sorry, so I missed. You proved it.
I didn't prove it. What I mean
It's
is,
experimental evidence.
I have experimental evidence. I don't know how to prove something like that. Yeah, I mean, I don't know how to prove something like if you run a greedy algorithm for a long time and it stays bounded, then it is bounded, even though
Numerically, you noticed that.
I noticed it numerically.
Up to 9, there is a difference.
Yeah, up till 9, the greedy algorithm seems to produce a bounded infinite walk. But then in dimension 9, it just blows up. Right. So that's I'm just saying that's what makes me think, that this is only going to get worse in higher dimensions. But I feel like if it was really a dense semigroup, there'd have to be these funny relations or funny long words that stayed very close to flats or something. Like somehow but this is why it's challenging to me. Like the symmetric space is so inhomogeneous, or not. That's not the right word, but you know what I mean. There's
Non-isotropic.
non-isotropic, yeah. That I sort of imagine that these long branches are just more or less twisting in some way, and they're staying away from any flat, and so I expect them to just go out. But I just have I think also this is probably algebraically beautiful. I just imagine that there's a lot of beautiful algebra hidden in this thing, but I don't understand it. I don't know how to prove it or anything. Yeah, but it seems like a beautiful object to me. Right, that's right. You can ask, when you divide by the nth rooted n's and how to get into SLNR, you kind of mess up the arithmetic, but you could imagine just sort of looking at the rational numbers you get, not scaling. And what is this thing?
Projective space or something.
Right, to look at some kind of projective action of this thing. Yeah, I'm guessing it's a beautiful thing. And maybe you're right. Yeah, you look at it mod, pianically or something. It has some structure. But yeah, well, I'm not done. I couldn't make any more progress. So that's all I have.
So that's time to stop the video recording.
Yeah. Anyway, well, thanks, guys.